Hello and welcome. My name is Devashish and this is an Ed Sharpener production. Welcome back to the channel. Apologies for the non-linear content, but this is a special video for my previous students where I was working earlier. More update on that. I will upload the video what I'm doing right now and what we will upload on the channel next. But this is the topic from EMFT, electromagnetic field theory, and we will continue with the general aptitude section as well as EMFT, and the topics will be continuous, I assure you that. So this is a video for my previous students, which is application of divergence theorem and Stokes theorem. So we are specifically looking at the applications, how divergence theorem and Stokes theorem can really be used. So let us understand what divergence theorem says. So divergence of A is given by del dot A, which is also given by the contour integral of A ds divided by del V, whereas limit del V tends to 0. So basically what we are trying to say is we are taking a dot product of vector A with the ds element. Ds is an area element. Now we want to find how much a vector field diverges out of the point. And for that we select a small closed surface which is a closed volume, so it can be looked as dv. As we tend the delta v towards 0, we can look at it as dv, and this is why a dot ds, or the vector field coming out of this surface, is given by del dot a. We are not looking at the proof of it, but this is how the statement of divergence theorem is given. When you put del v tending to 0, this becomes dv, and if you take it on the left hand side, you get this term, and on the numerator you have contour integral a dot ds. You get this contour because we have a closed surface. Whenever you have a dot ds, you can also compute the same integral by taking the divergence of the vector and computing with the volume integral. We will understand this better if we actually take up a problem. Let us see the problem. Now, here we are verifying the divergence theorem. The given figure is of a cylinder with rho equal to 1 and z equal to 1, where rho is nothing but the radius of the cylinder and z is the height of the cylinder. So this is height and this is rho. Both the values are 1. The d vector is given as 4 rho z arrow cap. Arrow cap is a unit vector and we wish to verify the divergence theorem. According to the statement of the divergence theorem, we have d dot ds equal to del dot d dv. Now we will calculate this term first. Now looking at d, we have the value and we don't know what is ds. ds is an elemental area for the given figure. Now we can split this term as d dot ds for the top surface plus d dot ds for the bottom surface and d dot ds for the curved surface. In these three segments, if we divide the surface integral, we put the same d value everywhere. Only thing that changes is ds, because in every direction the ds value is different. For a cylindrical coordinate system, we are using cylindrical coordinate system because we find the variables like rho and z, and that is why we are choosing the cylindrical coordinate system to solve this. And we will write ds in cylindrical coordinate system. We already know that for the elemental surface area along az cap direction, or this direction, is given by rho d phi d rho, and the unit vector is az cap. Remember, ds is a vector, area is a vector, it shows us the orientation. For the top surface, the orientation is upwards in az cap direction or in the positive z direction. For the bottom surface, similarly, only the direction changes. The magnitude of the area is same, rho d phi d rho az cap, but minus. Now we know that d is given as 4z rho a rho cap. A rho cap is in this direction. Let me show you that. So this is an elemental surface area on a curved surface, and this is the a rho direction, or the direction along the radius. So this is rho, and in the same direction you extend a rho cap. So basically, when you put d dot ds for top and bottom surface, you're ultimately doing a dot product of az cap and a rho cap, because the vector that is associated with d is given as 4z rho a rho cap, and if you do the dot product with rho d phi and d rho, then you have az cap, multiplication of a rho cap and az cap, the dot product is 0. So basically top and bottom surface integrals would be 0 in this case. Now the only thing that is remaining is d dot ds along curved surface. For the curved surface, the ds vector is given by dz rho d phi in a rho cap direction. More on this in the coming videos, how to compute the elemental area. So remember this for now. So computing the last integral, we have 4z rho a rho cap dot rho dz d phi a rho cap. Now arrow cap dot arrow cap is 1, remaining thing multiplies. So we have 4z rho square dz d phi. This is a double integral, as this is a surface area. So dz d phi gives you the double integration. So what we will do is we will compute the integration with respect to phi first, and then with respect to dz. So if you do the integration with respect to d phi, the additional term that we get is 4z rho square phi for the limits 0 to 2 pi. As this is a complete cylinder, the phi value would be from 0 to 2 pi. If this was only a half cylinder like that, then the value of phi would have been 0 to pi, but this is a complete cylinder, so this is 0 to 2 pi. If you solve this, you get 8 pi z rho square, and then we have to do the integration with respect to dz as well, that is remaining. So if you integrate this with dz, the limit from 0 to 1, we get 8 pi z square by 2 rho square as 4 pi rho square z square, and the values for rho and z will be given as 1, because that is the limit of it, 0 to 1. So we put the values of rho and z as 1, and we get 4 pi as the answer. Now we will remember this answer 4 pi, and we will try to solve the same problem with the divergence theorem. Let us see if we get the same answer. We will write the answer that we have got first, which is 4 pi. Now we have del dot d to be computed. Now in cylindrical coordinate system, the divergence of any vector d is given as 1 by rho del by del rho rho d rho. We won't write the unit vector, as the dot product of the del and d would give us the scalar. The second term would be 1 by rho del by del phi capital D phi plus del by del z of capital dz. Now the term that is given to us, we have that d vector is equal to 4z rho a rho cap. Now capital D rho is the coefficient of a rho cap. So this is nothing but d rho. Rest of the terms are 0. So 0 a phi cap plus 0 a z cap. So capital D phi and capital dz has 0. So we just need to compute this term here. So let us compute rho d rho first. So rho d rho is nothing but 4z rho square a rho cap. This is nothing but rho d rho. And now we will operate this with del by del rho. So we are differentiating this with respect to rho, which gives us 8z rho, and we have 1 by rho out, so which is 8z. So this is del dot d. According to divergence theorem, del dot d dv gives us the answer. Now del dot d is 8z, so this turns to 8z, and for the cylindrical coordinate system, dv is given as rho d phi dz d rho. So this is what a dv is. So this is a triple integral, so we will just write 3 integrals. Now we will integrate this with respect to rho first. We have 1 rho. If we integrate this with respect to rho, we get 8z rho square by 2, which is 4z rho square. And now with the limits of rho from 0 to 1, we get 0 to 1 as limit of rho. So it turns to 4z, and we have 2 more integrals to be computed now, d phi and dz. If we compute this again, for d phi, we get 0 to 2 pi. So we write 4z phi with 0 to 2 pi, and we have 8 pi z. And again, the last integral is remaining as 8 pi z dz. If you do this, we get 4 pi z square for the limits 0 to 1, because z is also 1, which varies from 0 to 1, and then we can compute it as 4 pi. So as we can see from the divergence theorem as well, we got the same answer, which is 4 pi. So basically, when we calculated the surface integrals for the top surface, bottom surface, and a curved surface, we were lucky this time because the integrals of top surface and the bottom surface were 0. But eventually this will not be the case every time, and if you apply divergence theorem instead, you save a lot of time not having to calculate the top, bottom, or curved surface, or many other surfaces which are required. So directly you can compute the dv and find out the answer with the divergence theorem. Hope you have understood. Now let us look at the Stokes theorem, where the line integral of the vector can relate to the surface integral of the curl of the vector. So this is the statement of the Stokes theorem, and we can prove it with a simple fact. Before that, let us understand what is the definition of the curl of the vector. For the definition of the curl of the vector is nothing but the circulation of a vector A around any point, how much the vector A rotates around that point. The physical significance of this is the topic for another video, and I will explain it. But for now, remember, if the curl is larger, the circulation of the vector around a point is larger. To find out the circulation of the vector around a point, what we do is we assume a particular area around a point, which is a closed path, and we find out the line integral around the path. When this is the closed path, we put a counter integral sign and we do this, and we want that this area to be minimum. So whatever area that we are talking about needs to tend to 0. So delta S tends to 0. So this is what we want. And this is the definition of the curl of the vector. Now we can understand this statement. This is an attempt to prove this Stokes theorem. We want to compute the circulation of vector field A which exists in this particular area. So we have the path ABCD and we wish to compute a circulation of vector field A around this path. Computing this around a larger area is equivalent to doing this. I'll explain you how. We will divide the whole area in different small areas. Every part of it has the area del sk, and the length around the path, each path, is lk. Let us say lk. That is again a closed path, so we have put a contour. The large line integral is equal to the small individual line integrals taken along the small paths for the same vector field. So if there are k such paths, the summation of k line integrals for the paths whose lengths are lk and such that we now multiply and divide by delta sk on numerator and denominator. So this is a valid statement. And now what we want is we take the limit of this term as del sk tends to 0. As we already know, this statement is true. So this whole statement, this part is nothing but del cross A, and as the summation is here, and if the limit is taken, the summation takes the form of the integral delta sk turns to ds, and already we have del cross A. So the Stokes theorem proof is descriptive, and you can give the theorem proof like that. You just need to define what del cross A is, and then you can prove it. So we are actually interested in applying the Stokes theorem, similar to how we applied the divergence theorem in previous slide. So let us look at the application of the Stokes theorem, how we can apply the Stokes theorem. Already we know the statement of the Stokes theorem as A dot dl for a closed surface gives the surface integral of del cross A. So now we will verify this Stokes theorem by first calculating this term and then this term, and then we will show that both the terms are equal. The A vector given to us is in Cartesian coordinate system, and it is x square ax cap minus xz ay cap minus y square az cap. The surface that is given to us is this. As you can see, the surface has the coordinates as, let us call them A, B, C and D. Now we need to compute the circulation along this path, the given path. So let us take this direction. You could take even the counterclockwise direction, but I will take the clockwise direction. I will tell you what happens if you change the direction. So you need to remember that while computing the line integral, we can split the line integral for the contour as A dot dl for path AB plus A dot dl for the path BC, A dot dl for the path CD, and A dot dl for the path DA, which closes the contour. Now only thing that changes according to this path is the limits, because while going from A to B, x value, y value and z value changes. I'll show you what dl is. We know what A is, so we can compute A dot dl. All these are vectors, so I'll just put the vector sign. We know that dl vector is given as dx ax cap plus dy ay cap plus dz az cap. A vector is this, so A dot dl would be x square and dx multiplication, x square dx, ax cap and ax cap gives 1, then we have minus x z dy, and ay gives 1, then we have the last term minus y square multiplied with the az cap term dz here, and then we have to take up the integration. Now we will take the integration along the path AB, BC, CD and DA. First we will compute the integration for the path AB, but before that let us compute the integration. So we get x cube by 3 minus x by z minus y square z. Now the integration remains the same, only thing that changes are the limits. For path A to B, the limit for this term, that is the x changes from 1 to 1. That means the limits for this term are 1 to 1. That means this term would be 0 for path AB. This term has the limits for y. So y changes from 0 to 0. Again this term would be 0. And for the last term again, minus y square z. This is the last term which has the limits for z, and z is changing from 0 to 1. So if you put the limits, you get the term minus y square. And for the path AB, the value of y, so this is x-axis, this is y-axis, this is z-axis, value of y on this path is 0 because this is the x-axis and y is 0 for path AB. So we will put y equal to 0. So the integral for a dot dl on the path AB is 0. So I'll write 0 here. If we have computed the integral for the path AB, we can compute the integral for path CD as well. Only thing that changes for the path CD is the limit for z is, instead of 0 to 1, it is 1 to 0. Rest of the limit are 1 to 1 and 1 to 1, which would be 0 again. So for this term, last term, instead of minus y square, we would have plus y square. And on this path, for the path CD, value of y is 1, as you can see. So for a dot dl on the path BC, we have 1 here, we have 0 here. We will compute the line integral for the path, say, BC now. So let us compute the line integral for path BC. X is changing from 1 to 1, so this term again will be 0. Y is changing from 0 to 1, so we need to see what is the value of this term. So y 0 to 1, we get minus x z, alright, and then you have z changing from 1 to 1. What is the value of x and z on this path? X is 1 and z is 1, so that gives you minus 1. So I'll write minus 1 here. Alright, now for the last term, for the path dA, only thing that changes is the limit of xyz, or the limit of y changes from 1 to 0 instead of 0 to 1 here, because we are going from 1 to 0 for the y value. All the other limits we are shifting from z to z as 0 to 0 and 1 to 1. Putting the limit for y here, which is this term, and y is changing from 1 to 0, what we get is x z instead of minus x z. And what is the value of x and z here? X is 1 but z is 0, so this would be 0. So a dot dl around the path dA is 0. So the addition of all these is 0, and the total answer for the counter line integral is 0 as well. And now we need to compute the same answer by calculating the cross product of del and A. Now let us look at the cross product of del and A, which is the curl of A. So we write AX cap, AY cap and AZ cap. Then we write dou by dou X, dou by dou Y and dou by dou Z. The first term, which is x square, then we write minus xz then we write minus y square. Now we compute del cross A. So we get the first term as ax cap, and then we have minus 2y, that is dou by dou y operated on minus y square, which gives minus 2y, and dou by dou z operated on minus xz, which gives 2y plus minus 2y plus x, because this is a minus sign over there. And then we have the next term as minus ay cap, and for minus ay cap we get dou by dou x operated on minus y square as 0, and dou by dou z operated on x square, which gives 0 again, so this is 0. For the last term az cap, we get dou by dou x operated on minus xz, which gives me minus z, and dou by dou y operated on x square gives 0. So we need to see now what is a ds vector, which we will multiply with del cross A. Now ds vector is an elemental area around for this path. So this area is facing the ax cap direction. This is x-axis, and probably minus ax direction. We took the circulation along this path. As you remember, this was the circulation which was clockwise. If you put the right hand thumb rule, if you rotate your 4 fingers and put the thumb in the direction of the orientation of the area, you have to rotate your fingers around the rotation of the circulation that we have taken. So you will find that the orientation of the area becomes minus ax cap. So basically ds is having the direction of minus ax cap. What is the magnitude of the area which faces ax cap or minus ax cap? It is dy dz. We will take up one more session on this. So basically we have the ds area as dy dz ax cap, but with a minus sign. This minus sign has come because we have taken the clockwise direction. If we would have taken the counterclockwise direction like this, then there wouldn't be this minus sign. Now the direction of the ds is ax cap, which would multiply only with the first term. This is a cross product, and then we take the dot product with the ds. So ds is in ax cap direction, so we would only consider the term which is in ax cap direction. So if you compute that, you get minus 2y plus x, and then you have dy dz and minus sign. Taking the double integral again, if you compute the integration with respect to dz first, you get minus 2yz plus xz. The limit of z is from 0 to 1. So everywhere you can see that z is varying from 0 to 1. So putting the limits, you get the same answer, minus 2y plus x again. Now you need to integrate this again with respect to dy, and not to forget the minus sign which is outside, so I'll just put it inside. So 2y minus x dy, this is what we have now. If we integrate now, we get 2y square by 2 minus xy, and if we put the limits for the y, we get 0 to 1 again. So that is 1 minus x. Again, the x value for this particular area that we are considering, it is situated at x equal to 1. Every point is situated at x equal to 1, so x will be 1. So 1 minus x is nothing but 1 minus 1, which is 0 in this case. So this is how we have verified that the answer from the Stokes theorem is also 0. and the answer with the line integral is also 0. So this is what we have verified. The contour integral a dot dl for the path ABCD that we took is 0, and it is also 0 if we take up the cross product with A and then take the ds vector dot product. So now this is how you verify the line integral and the surface integral for Stokes theorem. As we saw that for the line integral we needed to calculate 4 separate integrals along the 4 different paths, but when we took the surface integral there were only one double integral, which was not so time consuming. You will often get complex paths and complex loops, and in those cases the Stokes theorem is very important. So concluding that the divergence theorem relates the surface integral to volume integral, and for the Stokes theorem we can conclude that it relates the line integral of a vector with the surface integral of the vector. I hope you have understood, and we will keep posting such videos on EMFT, and we'll be back with the continuous videos on general aptitude section. And I'll give a small update also on what I have been through and we have been through as a team. Keep watching the videos. Please subscribe to the channel because a lot of content is coming up, and share and like the video as well, because this is a very important content with respect to GATE and other examinations in engineering. Thank you so much for watching. जल्दी ही मिलेंगे, तब तक के लिए ज्ञान पीते रहिए.